The final two rules that we are going to acquire in this course are identity introduction and identity elimination. The basic idea motivating identity elimination is as follows. If you know that A and B are the same object, and you know that A is F, then you can infer that B is F. So for example, if you know that Superman is Clark Kent, and you know that Superman flies, then you can conclude that Clark Kent flies. Formally, this rule looks as follows. If in line M of your proof you have the identity statement A equals B, and in line N of your proof you have a sentence that ascribes a property to A. So A has the property of being A in this case. You can then infer that B has the very same property. So B has the property of being A as well. And you can justify this inference by means of identity elimination applied to lines M and N. Now this rule works symmetrically, meaning you can apply it to either the name A or the name B. Suppose, for example, that in line M of your proof, you again have the identity statement A equals B, and in line N of your proof, you have a sentence that ascribes the property A to B. You can then infer that the object A has this property as well, and justify this inference by means of identity elimination applied to lines M and N. So here are a few examples of correct applications of identity elimination. Let's start in the top left corner. Suppose that in line M we have the sentence A equals B, and in line M we have the sentence either FA or all X are G. You can then infer that either FB or all X are G and justify this inference by identity elimination applied to lines M and N. Now, this works symmetrically. Suppose that in line M we have the sentence A equals B, and in line N we have the sentence FB or all X are G. You can then infer that either FA or all X are G and justify this inference by means of identity elimination applied to lines M and N. Now, to give you a third example, let's look at the top right corner. Suppose in line M we have the sentence A equals B, and in line N we have the sentence LAA. You can then infer LBA and justify this inference by identity elimination applied to lines M and N. And to give you a final example, suppose that in line M we have the sentence A equals B, and in line N we have the sentence LAA. You can then infer LBB and justify this inference by means of identity elimination applied to lines M and N. Now, the difference between the third and the fourth example here is that in the third example, we only replaced one of the occurrences of A by means of the name B, but in the fourth example, we replaced both occurrences of the name A with the name B. Both are correct applications of the rule identity elimination. Now, identity introduction is an incredibly easy rule of inference. The basic idea motivating this rule is as follows. For any object C, C is identical to itself. So for example, Atari is identical to himself. Formally, the rule looks like this. At any point in your proof, you can assert an identity of the form A equals A and justify this inference by means of identity introduction. So you don't have to use the name A. You can also introduce the sentence B equals B, or C equals C, or D equals D, using any name whatsoever, and justify that new sentence, that new line in your proof by means of identity introduction. So let's look at one example of a proof that makes use of both identity introduction and identity elimination. In line 1, we start with the supposition that A equals B. In line 2, we assert that A equals A and justify this assertion by means of identity introduction. In line 3, we can then infer that B equals A and justify this inference by means of identity elimination applied to lines 1 and 2. In line 4, we can then infer that if A equals B and then B equals A, and justify this inference by means of conditional introduction applied to lines 1 to 3. We can then infer that for all y, if y equals b, then b equals y, and justify this inference by means of universal introduction applied to line 4. And then in the final step, we can infer that for all x and for all y, if y equals x, then x equals y. So what we have proven here is the so-called symmetry of identity, meaning that for any two objects whatsoever, if y is identical to x, then it must be the case that x is also identical to y.